we are back. So I want to tell you another story. So recently I took down my holiday lights. And before that, I had to go up on or near the roof to clean out the gutter. And after I come back, I'm going to have to go and basically spray demossing spray on my roof. So I have a lot of projects where I have to work on a ladder. So I lean against the ladder so it touches essentially the wall of the house, or basically the ground. And those are two different surfaces with two different coefficients of friction. So I use a 4-meter ladder. My mass, hopefully, after workout, is about 100 kilograms. The angle between my ladder and the wall is about 18 degrees. The coefficient of friction with the wall and the ladder is pretty robust, so about 0.7. And I want you to tell me what is the coefficient of friction that I need on the ground to prevent the ladder from moving. Do I have to lose weight? Help me. So let's go ahead and let's start to, again, what's our first step in our problem-solving algorithm? Idealize our system. So if I think about it, I'm standing on the ladder. So I have here my coefficient of friction 1 is 0.7. I don't know what this coefficient of friction 2 is here. I've got this angle theta. I'm going to have some weight, and my weight will just be equal to mg. What else? I would expect that there is some reaction forces here and here, but this is a pretty good ideal system. So idealize the system. What's our next step? Coordinate system. Forget this. This is weight. Coordinate system here, and I know that there's going to be a reaction force like this, F1. Reaction force here, F2. Fantastic. Now, friction. Friction needs to be tangent to the surface, but it also needs to be opposite the direction of impending motion. So if this ladder falls and slips, the motion is going to go this way, and then the motion will go down here. So my friction has to oppose this motion. So we get F1, not F1. We have F3 right here, which is our friction opposing the sliding the ladder down. And we have F4 right here, which opposes the ladder slipping out in this direction. So I've got my free body diagram. I freed the body. Now it's time to write out our equilibrium expressions. So I'm going to, well, first off, I'm going to go ahead and clear my kernel. And I'm going to start to define some values that I know. So I'm going to just give it a ladder. So I know my mass, hopefully, is 100 kilograms. My G is equal to 9.8. My weight is equal to m dot G. Oops. All right. What else do we know? We know that theta is equal to, I believe, theta is equal to 18. Theta is equal to 18. What else do we know in this system? We know that U1 is equal to 0.7. I also know that my F3 is equal to mu1 dot F1, and I know that my F4, you can see that over here. Let's scroll down. My F4 is equal to mu2 times F2. So I think those are all the knowns so far. So let's go ahead and let's set up our expressions. So f sub x equals 0. I'm F1, positive direction, minus F4, negative direction. Fy equals 0, set equal to F3 plus F2 minus weight. Excellent. Now I need to do my moment. So I'm going to choose my moment right here. And we have this angle theta, and we have, it's a 4-meter value here. And we also know this is 1.8, the distance right here. So let's look at weight first. I draw my line of action, the perpendicular distance from my origin. And if I do my right-hand rule, I can see that that should be a, no, where'd it go? Don't quit on me. So actually we're gonna have to, yeah, here, let's pull this out, pull this back here. Hopefully it decides it wants to come out. Nope. I'm gonna have to, actually what we'll do is we'll just set this up somewhat side by side. Try right here. Now let's go ahead. Isn't this just fun? There we go. All right, now we're all happy. So the moment about my point equals 0. So first it's going to be weight times 1.8. That wasn't an intended pun. What about my f sub 1? So my f sub 1, this is my line of action. The perpendicular distance will simply be, and if I look at that, I'm going to have to do into the board, so that's going to be a negative. So minus f sub 1 times 4 times sine of theta degree, because that's our distance. And what about f sub 3? Again, line of action, perpendicular distance from that value there. It's going to be what? It is going to be, and then I actually, if you look at it, I have to go into the board. So again, minus f3 times 4 times cosine of theta degree. And looks pretty nice so far. How many unknowns? F1, F2, U2? Not the band. Let's solve. Fx, Fy, MP. What do you know? But that's a pretty it's a pretty frictional surface, so unfortunately I think the answer is I'm gonna have to lose some weight. But I'll do it. I'll do it just for you all. But anyways, that's our answer. That's our solution. So that is how we can approach solving problems like this. So next time, we are going to get into a very important question that I want you to help with my research. And let's get rolling, or actually let's not roll. And let's see if we can actually apply this to a very unique, more kind of biomechanical system. But help me, please. I need this for my research. All right, I'll see you in the next video. Thanks. Bye.